renewable energy, coal with carbon capture and storage, and nuclear power. I personally believe we need to do all four of these things. I don't think we can afford to take anything off the table because climate change has become so serious and we've been so delinquent in addressing it. But at the conference that we held, it was sponsored by the American Solar Energy Society, so we focused on the first two, energy efficiency and in particular the various renewable energy sources. So this came out of a conference that was held back in 2006. It's called the ASIS, American Solar Energy Society Tackling Climate Change Study. And these are the technologies we looked at: geothermal power, photovoltaics, biofuels, biomass power, concentrating solar power, wind, and also efficiency. And this was different from most studies. Most studies are top-down studies where analysts look at all the possibilities and compare them all. Here we had each person who was an expert in their technology area, from the bottom up, estimate what they thought their technology could do by the year 2030 for reducing U.S. carbon emissions. So for energy efficiency, we see 40% of our energy is used in buildings, 30% in transportation, 30% in industry. This was a study done by Joel Swisher, who at the time was working for the Rocky Mountain Institute, Amory Lovin's organization. You can see that in buildings we can have improved envelope design, daylighting, better lights, building and appliance efficiency standards. In transportation, lighter weight vehicles, plug-in hybrid electric vehicles. In industry, heat recovery, better motors, and so-called combined heat and power, where we generate power and use the waste heat for industrial applications. This is an enormous area. There was a study done by McKinsey where they looked at the various costs of the various ways to reduce carbon emissions. And I point this out because the y-axis, this was done for a European company, the y-axis is the number of euros it would cost per ton of carbon dioxide emissions that are displaced. And what you can see is a lot of these have negative costs. They actually save money, and a lot of these are energy efficiency measures. So energy efficiency can save a lot of money, and you'll see that later. Anyway, when we looked at those sectors of energy efficiency, electricity, oil, and gas, large savings at low cost for all of them. When you add them all up, 688 million tons of carbon per year savings, which is 57%, I believe, of the total savings that we saw in the study. So efficiency, when people say efficiency is the low-hanging fruit, it's a thing we really need to pursue first, they're right. It's the biggest one. We looked at concentrating solar power, where you use the sun's heat to boil water at high temperatures and run a steam cycle and run a steam turbine, much as you would with a coal plant or natural gas plant, natural combined cycle plant. There's been over 350 megawatts of concentrating solar power operating successfully for 20 years in the Mojave Desert. There's a plant that was completed about 2 years ago outside of Las Vegas, operating very successfully, and there are many, many more plants that are planned in the near future. There's a 280 megawatt plant scheduled to be built starting in January of 2011 with 6 hours of thermal storage that can provide heat after the sun sets. That would provide electricity to Phoenix. So you can see here the jobs that it creates during construction and permanent when the plant is running. Anyway, we concluded in this study that we could provide 80,000 megawatts of concentrating solar power by 2030. It costs ranging from 14 cents or so per kilowatt hour today down to 6 cents per kilowatt hour as this technology comes down in cost. That would save 63 million tons of carbon per year. We looked at roof-mounted photovoltaics. And here, you know, in concentrating solar power, the resource is mostly in the southwest because we need clear skies to optically focus the sunlight and get high temperatures. Most photovoltaics collects both direct solar radiation and diffuse radiation that you get when the skies are hazy. And so it's more applicable for all parts of the country. But we looked at roof-mounted photovoltaics saving 200,000 megawatts peak by 2030 at cost between roughly 28 cents a kilowatt hour today down to 6 cents by 2030. And that would save another 63 million tons of carbon per year. We looked at wind power. This has been a big success story in the U.S. We've passed 35,000 megawatts of wind power installed in the U.S. right now. We looked at providing 20% of our grid electricity or grid energy from wind by 2030. That would be 245,000 megawatts. That costs between 3 and 7 cents per kilowatt hour. This is the biggest renewable energy contributor, 181 million tons of carbon per year. We looked at biomass and biofuels. This is where biomass is distributed around the U.S. See a lot in California, a lot in the Midwest, but also a lot in the Southeast and even the Northeast to a certain extent. Biomass power is a great way to displace carbon because you can directly compete against coal plants. You can burn biomass. You can burn it with coal to displace some coal. You can also gasify biomass and burn the gas to run a gas turbine. If you do that, you can combine that with carbon sequestration and storage, where now biomass, instead of being carbon neutral, biomass is usually considered carbon neutral. Basically, you put carbon dioxide into the atmosphere when you burn the biomass, but when the plants are growing, they take that carbon dioxide back out of the atmosphere. Well, imagine if you burn biomass, or if you gasified biomass, you capture the carbon and geologically sequestered it, and then ran a gas turbine using hydrogen that you get from the biomass. That would be a net extractor of carbon from the environment. So it would actually be carbon negative. Anyway, biomass power, we looked at using wood residues and municipal discards, providing 45,000 megawatts by 2030, a cost between 8 and 5 cents a kilowatt hour. That would save 75 million tons of carbon per year. And finally, in biofuel savings, looking at producing cellulosic ethanol, that is ethanol from crop residues and energy crops. This would not compete against against food crops. Save 28 billion gallons of gasoline in 2030. It costs between about $4 a gallon of gas equivalent, down to about $1 by 2030. That would save 58 million tons of carbon per year. And the last technology we looked at is a geothermal. This is a geothermal power plant in Northern California. Geothermal resources are very strong in the western United States. We looked at providing 50,000 megawatts by 2030, 25% from existing sources, 25% from expanded sources, and 50% from oil and gas wells at costs from 5 to 10 cents a kilowatt hour. And that would save 83 million tons of carbon per year. So putting all this together, we have a little map here, and the map shows us where we would need to be on the path for between a 60% reduction and an 80% reduction by mid-century, and that's what those bars represent. And if we just populate this map with the various solutions, energy efficiency, a very, very big one you can see there. We add wind, we add photovoltaics, concentrating solar power, biofuels and biomass, and geothermal, and we're in the ballpark of where we need to be just with all those technologies. This is the same thing on a wedges chart, and it shows the top graph. It shows U.S. carbon emissions out to the year 2030 as predicted by our Energy Information Administration. If we want to preserve the polar ice caps, if we want to start to mitigate climate change, we clearly cannot go marching up this path. But we find that with a growing economy, with energy efficiency, we can essentially levelize out our carbon emissions. That's what this big wedge is. And below that, if we're going to get serious about actually lowering carbon dioxide emissions, not just holding them level, then we need to use these various renewables, and we've got wind, biofuels, biomass, photovoltaics, concentrating solar power, and geothermal. After our study was done, I looked at the costs that each of the experts came up with, and I wanted to come up with, between now and 2030, what the annual cost to the U.S. economy would be. To do that, I needed to look at the difference. What each would cost, for example, in terms of electricity, versus what it's displacing, conventional electricity. So I looked at that differential cost, and I figured out on an annualized basis how much it would cost our economy to do these things. And so if I look at what it costs, deploying all that geothermal would cost us $2 billion a year between now and 2030. Concentrating solar, $7 billion a year, $5 billion a year for biomass, $3